Today we're happy to have Hsing-Yi Lai
Yes.
to tell us about the phenomenology of monopoles.
All right. Thanks to have me here. Feel free to interrupt me anytime, as I'm open to any question, especially those that might show up in the call. So, this is what I've been doing with John in here. It's about dark matter monopole, and I will first introduce what that is, and to study it, we are using a newly developed method to compute scattering amplitude, which is the constructed method. We will use it to show that the single photon production of this dark monopole pair will be 0, and then I will discuss a little bit about how to compute the total cross-section at the Large Hadron Collider to produce this dark monopole pair, and then give a summary. So, what is magnetic monopole? Is a thing with just N or south pole, and as long as I know, William Gilbert is already trying to find monopole back in 1600. So this is an image on his book showing he tried to find monopole by cutting magnet in half, and he doesn't find it. But we know everybody kind of predicts that monopole should be 6. But
He
so
just
far,
plagiarized that from someone else's book.
oh really? So I know there's
It's fine.
Okay.
There was no peer review back then.
Is it actually from other people's book?
Oh, he stole it, yes.
Okay, because I tried to read the older book, but I didn't find the image, so I thought it's this book. I don't want to give.
It's fine. I'm not trying to derail your talk.
I do want to give correct information. Anyway.
Well, he published this in 1600. That's correct.
Okay. All right. So, and on the other hand, dark matter. People have observed the effect of dark matter on galaxy back in 1930s, but no one really recognized this is a real thing until like 1970. So it's kind of like nobody really expects it's there, but we know it's true. So both topics are fascinating. If we combine it, it will be even more fascinating. So that's why we should study dark magnetic monopole, which is like dark matter with magnetic charge.
You
But,
might
yeah.
want to add Vera Rubin's name to this second side, since you
Because
put William Gilbert's name on the left side.
you know,
Give credit to this dead white guy, and then Vera Rubin makes this fundamental discovery, and she doesn't get her name on it.
for this one?
Yeah, not for the picture, but for the 1970s.
Oh, okay. 1930 or 70.
70.
Oh.
Vera Rubin.
Okay. So, what is magnetic charge? It's easy to understand if you are just looking at classical level. You just point at the Maxwell equation and say, this is magnetic charge, and this is magnetic current. And if your particle has a magnetic charge, you get an extra term in your Lorentz force. So that's classical level. It's easy to understand, but we want to do quantum theory. So the way we know how to generalize this to quantum theory is to look at the discrete symmetries, which is the charge conjugation, parity, and time reversal. So let's consider a simple case, which you have a line of electric particle moving this way, and you have, so these particles generate magnetic field. If you have a magnetic charge with positive charge, which I denote as the north pole, then the force you get will be in the same direction as the magnetic field, like this. So if we do a charge conjugation, then it will swap all the particle with antiparticle. Negative charge moving that way generates magnetic field in the opposite direction, but because the magnetic charge also changed to the opposite sign, the force you get is in the same direction. So indeed, after we add magnetic charge to our QED theory, it is still preserving the symmetry under charge conjugation. That is fine. The interesting thing happens when you look at time reversal and parity. So for time reversal, the velocity of the electric charges will change direction, which causes the magnetic field to switch direction. But force should be invariant under time reversal. So if the force should still point this way, the magnetic charge must change into the antiparticle. So that's the difference between electric and magnetic particle under time reversal. Electric particle stays the same, but time reversal will swap magnetic particle into its antiparticle. Same with parity. We see the velocity change direction, but the magnetic field is a pseudo vector and it doesn't change direction under parity. The force should change direction under parity, which means that the magnetic charge should also get swapped under parity. So that's the difference between electric and magnetic charge. The parity and time reversal will swap magnetic charge, but not the electric charge. So that's the difference. And we can incorporate this to a Lagrangian level. When we want to look at the interaction Lagrangian, we know the electric and magnetic charge both interact with photon because they are electromagnetic interactions. But if they interact with photon in the same way, then there's no difference. So I know they must interact with different way, which I just write as A and B. They are different. And exactly how they are different is that under parity, we know the electric charge or the electric current will get a minus sign, while the magnetic current will get an extra minus sign because it also got swapped because the magnetic charge also gets swapped, so there's this extra minus sign. So if both interaction Lagrangian need to preserve parity, then it means that this A potential should have A minus sign under parity, while this B potential should not have a minus sign, or it should have a positive sign under parity. And what it means is that this A potential should be built out from the two photon helicity added together, while for the B potential, photon with different helicity should have a minus sign between them. And that's the difference between electric and magnetic particle at the quantum field theory level. They couple to the plus and minus helicity photon in a different way. And all of this has been worked out by Weber in 1965.
I thought there's some S-duality which swap the electric charge and magnetic charge. But you also redefine the parity or time reversal.
There is a
photon transforms by phase under S-duality.
Yes. I would just say if you want your definition of parity.
You're swapping A and B, right?
Yeah, I mean, you say under this thing, the charge, the electric charge doesn't change, magnetic charge change from north to south. But in a different picture is that the magnetic charge doesn't change.
Parity changes under duality.
Huh?
Parity transformation is
so
different.
So you say you have to redefine your parity.
Yeah, that's in the Cyber paper.
And the time reversal too.
I'm confused about the time reversal argument, but definitely the parity.
Should I go read that paper or?
Eventually, not right now.
Okay. Alright, so this minus sign between different helicity for magnetic charge is important for later. Okay. So now we know what is a dark magnetic monopole. It's just a dark matter candidate that transforms like magnetic charge under CPT. So if we want to study this model using Lagrangian, Zwenziger had shown in 1971 that your Lagrangian need to look like this. We know the photon should couple with electric and magnetic current with different ways, but then if you have two vector potential, there's 8 degrees of freedom. You have to project this 8 degree of freedom down to 2 with this constant vector n. And that's why your Lagrangian looks way more complicated than just regular QED Lagrangian. But it can be done. This will give you the same Maxwell equation. And if we want to have a dark vector, then we have to copy this Lagrangian and add a capital D on all the electric charge and photons. So that's this Lagrangian for the dark sector. And then we can introduce a kinetic mixing like this. So this will give some interaction, a small interaction between the visible sector and the dark sector. Here you see this is the field strength tensor that we're familiar with, but in terms of this two vector potential, you have to use this n vector to express the whole thing like this. So in our theory, there's magnetic charge. So the Lagrangian looks longer, but this dark photon should be the same as the dark photon other people are talking about. It's just a U1 gauge field, unless there's multiple dark sector, but let's just say this one. And we will consider just the visible electric charge and dark magnetic charge. So we will have no visible magnetic charge and no dark electric charge in the slides later. All of this has been done by John and Chris Baharan before I came here. So to study the interaction, we can diagonalize the field in the visible and the dark sector so that the kinetic mixing term will be gone after you diagonalize the field. And as a result, you will see that the visible photon will have a small coupling to the dark magnetic current, and the dark photon will have a small coupling to the visible electric current. There's an important thing that after this diagonalization, there will be a phase difference between a coupling caused by photon and coupling caused by dark photon. This is going to be important. Again, this is done by others. So we can study this dark monopole using Lagrangian and field theory, but still that constant vector will cause a lot of trouble in calculation. People have resolved those trouble, but still it's kind of messy. It's not messy, it's like it's hard to deal with this n vector. So it will be good if we can have some other way that doesn't need field theory, so we don't need to deal with this n vector. And indeed, there are some other way to calculate scattering amplitude in the modern amplitude program. And the one we're going to introduce is this constructive method proposed by Akane Hamed, Huang, and Huang. So in this formalism, the trick is to allow the momentum of the particle to be complex. If you can have complex momentum, then you can have well-defined three-point amplitude such that all the particle is unshelled, but the full momentum is still conserved. We all learned that you cannot absorb one photon with one electron because you cannot do both at the same time, but if you allow the momentum to be complex, you can have a well-defined three-point amplitude. Then if you want a higher point amplitude, all you need to do is to multiply the three-point amplitudes, which we say we glue them. And after you glue the three-point amplitude, the thing you get is called the residue. And then it becomes a residue of a four-point particle. For three-point amplitude, you need to have unshelled intermediate particle, which the expression will depend on its momentum. But after you go to a four-point residue, you no longer need to keep the internal photon unshelled anymore because you only care about external particle. So you can use momentum conservation to substitute this internal particle's momentum with external particle's momentum. Then you can say, now I have an expression with just external momentum, and then I can relax the momentum back to real value. And then that's the residue of a four-point of a 4-point amplitude, then you just put the pole back corresponding to the propagator of this internal particle, and then you have your 4-point amplitude. And you see all of this can be done without using field theory, and all we need is the 3-point amplitudes to define the theory. And to build up this 3-point,
I would say you're doing it without using a Lagrangian, maybe.
Without doing
It's
that
still
point.
just a different way of doing field theory. Okay. I think, when you say.
Okay, so to build out these 3-point amplitudes, what we need is the spinor helicity variables defined by contracting the full momentum with these sigma matrices. So the sigma matrices are the polymetrics in the spatial component and a 2x2 unit matrix for the time component. For massless particle, this 2x2 matrix can be decomposed into a 2x1 column vector direct product with a 1x2 row vector. And for massive particle, you have to add 2 pairs of them using the Dirichlet dot tensor. So you can see that these spinors are not uniquely defined by the momentum. You can do a U1 transformation. We want to keep the normalization, so it's a U1 transformation, and this will not change the momentum of the particle. This U1 transformation actually corresponds to the little group of massive particle. And for massive particle, the little group is SU2, and you can see indeed we can perform a SU2 transformation to the spinors, but that will not change the momentum of the particle. So to build up the 3-point amplitude, the key is that we use the spinor helicity variables such that the little group transformation property of the particles are respected. And here we will write the momentum, we will write the spinor as just the number of the particle and drop the p for simplicity. And for massless particle, a square spinor is like having half helicity, and an angle spinor is like a minus half helicity. So if you have a massless particle with helicity h1, the difference of their power should add up to h1, and that's how you have a correct little group transformation property for the massless particle. Similar things happens to the massive particle. For the massive particle, the little group is carried by this SU2 index. The angle and square doesn't really matter. As long as you have a SU2 index, then it transforms in the same way under the little group. So what you can see is that if you have totally 2s of this SU2 index and you fully symmetrize it, then the unique combination of this index will have, there will be 2s plus 1 of distinct combination, which correspond to the 2s plus 1 amount of spin states of that particle. So if you just symmetrize it, it will have a correct little group transformation property for massive particle. And for simplicity, we just bold the number, meaning that you symmetrize all the combination of the little group index. And to make sure the 3-point amplitude is Lorentz invariant, you need to contract the left-handed spinor index with left-handed and right-handed with right-handed. So you can have expressions like angle, square. The momentum have a left-handed and right-handed spinor index, so you can contract it with square and angle, but you cannot have expressions like this. So this is how we construct 3-point amplitude. And the thing becomes interesting when we look at a 3-point amplitude which 2 of the particles have the same mass and 1 is massless. What happens in this case is that the spinors are not entirely independent to each self. So it's like you have fewer elements you can use to build up your 3-point amplitude. But luckily, there's a proportional constant between the spinors, and it actually carries some information. to write this proportional constant as a number, you contract both sides with a arbitrary reference spinor, let's call it Q, and then you can express the proportional constant like this, which we call it the X factor. So if you look at this X factor, the top has a square K, where K is the momentum of the massless particle, and the bottom is a angle K. So together, this thing carries a +1 helicity for this massless particle. So if this amplitude has a massless particle with helicity h, then the 3-point amplitude should go like x to the power of h. And you can show that the inverse can be written like this, which we call it the x tilde. So x and x tilde is kind of like the plus and minus helicity of this massless particle. So what will happen later is that you will see this arbitrary reference vector q actually become something like the n vector in Schrodinger's Lagrangian. You'll see that later. But for now, if we want to use this 3-point amplitude to calculate 4-point by gluing the massless particle, then you will have to remove the k and q from the expression. And this turns out to be kind of hard. So let's look at the simplest example. This is the simplest amplitude you can calculate in your quantum field theory class. If you write the result in spinor helicity variable, it looks like this, where S is the Manos-Dehn variable. And if you want to calculate this using constructive method, then you glue the 3-point amplitude and sum over plus and minus helicity for the internal photon. So that gives you these two terms. Because the photon has spin 1, so you see there's one X factor for both 3-point amplitude, and the 1, 2, 3, 4 give you the little group transformation property for the external spin hat fermions. So our plan is to apply this constructive method to scattering amplitude involving magnetic particle. And before we do that, we should check it works for just the standard model case. And it turns out that for this case, it is not that easy. So this group, by Christensen and the collaborator, had published a paper about a year and a half ago saying that there's a challenge when you try to deduce this expression. To get the 4-point amplitude, you want to get the X factor out of the expression and turn them into the momentum of external particles. So what they've shown is that this equals this, which is not the Feynman result. And so there's a challenge, and this is not easy because no one has solved it for like a year until us, and it ended up getting published at Nuclear Physics B. So what me, Dario, and John have done is to look at this problem using old-fashioned probability theory, and it turns out that the expression that Christensen got is actually the Feynman rule result plus a term proportional to S, which will be 0 if everything is still on shell. So if you drop the term, then they agree and constructive method works. So if you want to know more about the detail, I can talk about it. But anyway, we've shown that this constructive method do work for just the electric particle case. And later this year, Christensen had shown that it actually works for all the standard model cases. So constructive method do work, and let's try to apply it to magnetic particles. So the thing for magnetic particle is that the parity transformation property is different. But the constructive method doesn't really care about parity. It cares about energy conservation, momentum conservation, angular momentum conservation, and it can be used to calculate theories that either conserve parity or violate parity, like the weak interaction. So we have to extend the 3-point amplitude in a way such that it can have a definite parity. So what we do is we apply a superposition between plus and minus helicity so that the thing becomes a state that transforms under the parity with a definite property. So photon has a -1 intrinsic parity, these two just swap helicity for the photon, but because there's a intrinsic parity of -1 for the photon, this whole thing is a parity odd 3-point amplitude. And if you subtract them, it becomes parity even. This I is there so that these two looks the same at the bottom, but it's just a overall phase for the amplitude. It doesn't change the physics. So we should check that this extension still gives the correct result for just a simple case. And you see when we glue these two, so the rule is that you should just glue minus plus and plus minus because these are helicity. Different helicity means the angular momentum is actually in the same direction because we are using all incoming convention. The direction of momentum is different for these two. So opposite helicity means the same angular momentum. And angular momentum must be conserved. So even though there are some cross terms, but if you encounter plus plus or minus minus, you just don't glue them and you drop them. And you see under this rule, we do reproduce the same result for electric and electric case. And for magnetic to magnetic, we glue the parity even states, and you see this plus minus, minus plus, do give you the same contribution as electric case, which makes sense. Like if you have electric to electric amplitude, it should look the same as magnetic and magnetic amplitude. So it looks like our extension will work, and if we want to calculate electric to magnetic, then we just glue a parity odd with parity even 3-point amplitude. So before we do that, let's first discuss the possible JPC for the bound state of electric particle pair and magnetic particle pair. So all of this have been done by John and Chris. What you're seeing, look at here is the JPC for different states and for electric and magnetic particle for fermion and scalar. So photon has angular momentum 1 and charge conjugation minus 1, so you must have 1 and minus sign for J and C. But for parity, you can have plus or minus.
When you say fermion scalar, you mean the state, the two particles both are fermion, or say the bound state?
The bound state, so it's both particles are fermion. Fermion bound state.
Okay.
Yeah, the scalar bound state. Yeah, they have to be antiparticle of each other. Yeah, so what we are interested in right now is the process like this, which you glue, which electric particle annihilate and produce a magnetic particle through a photon. That's what we're trying to calculate right now. So if you look at the JPC of the bound state, first of all, we want JPC to be conserved. So you only glue the bound states that have the same JPC. So you only glue blue with blue or red with red. So you can see if we just want JPC to be conserved, it is possible to have electric particle going to magnetic particle or the other way around. It's just that if you want to look at the blue case, then all the magnetic particles should be matched to the fermionic 1 plus minus JPC, which has singlet state for the spin configuration of the two fermion. And on the other way, it's the magnetic particle that must have spin singlet. So if you look at the matching JPC, then they must have either electric or magnetic side with a fermionic singlet state. And so we take that in mind and do the calculation. Like I said, for electric to magnetic, you glue the parity odd and parity even 3-point amplitude. Yeah. Sorry? Yeah.
Okay, you see, if you want to go from the electric pair to magnetic pair,
Yes.
you can only go from blue to blue and then red to red.
Yes.
Okay. Then the spin, you see from spin, So that means if you start with electron positron,
Yeah.
uh,
It's going to be electric fermion, the reference.
if I take blue, that means it can only go to scalar because only that one spin is one.
So if you pick blue for electric particle, then,
You can only go to that one.
or you can also go to fermion with magnetic charge.
Oh,
So it's like this can go to here, here, or here, and this can go to here, or this can go to here, here, or here.
okay.
Alright, so as I said, for electric to magnetic, you want to glue parity out 3-point amplitude with parity even. And that gives you this minus sign for the first term and positive sign for the second term, which I factor out the overall minus sign. You see, it's kind of like what Weber said. If you have magnetic particle here, then compared to electric amplitude, different helicity just give you a sign swap. So this agrees with what Weber says. And what we need to calculate for, let's say, fermionic signet, because we said one of the side must be singlet. So let's take the fermion side. Let's take the electric side to be fermion signet. And for the magnetic side, let's take it to be scalar just for simplicity. Then this term will look like this. The x factor is just for the spin 1 of photons, and because only the electric particle is fermion, you have 1, 2, but not 3, 4. Here, this Levitsky-Flat tensor is to anti-symmetrize the spin of electric fermions so that you have a single state. So this is the residue if we want to calculate this process. And for this combination, you can show that this subtraction equals this, which you see the Q comes from the X factors, same with the K. The spinor of the electric particles becomes something like this, which together is a 4 vector, and you have the momentum of the force particle with the Levitsky-Flat tensor here. And you can express this combination in terms of the Dirac spinors you are more familiar with, which this expression is the same as what you get using Schrödinger's Lagrangian. So it looks like we are on the right track.
The difference is, Swansger said the reference vector had to be space-like,
Yes.
and the X factor said the reference vector had to be null.
Yes.
So
So yeah, there's this small difference. So in Schrödinger's Lagrangian, so you see this Q corresponds to the N in Schrödinger's Lagrangian, and in the Lagrangian formalism, the N has to be space-like. But here, Q is just a mu vector that came from the definition of X.
but it had to be a null vector.
Yeah, it's a like mu vector.
So you get Lorentz invariant amplitude, even though you started with some special assumption.
What does that mean when they agree? They don't agree. You have no vector. So Schrödinger's Lagrangian cannot be formally with, can only be done with space-like vector.
That's what people think, yeah.
Is that true? What's wrong if you don't do that?
I thought there was some problem with the quantization. But
So you're
Schwartz and Sen have an alternate Lagrangian where the reference vector can only be time-like. you also get the same amplitude squared from all three calculations. So they agree in that sense, because physical answers don't depend on the reference vector.
So, but P and the subscript 4.
Yeah, it's the momentum of the fourth particle.
And what about K? K is the...
K is P1 plus P2 is the momentum of the photon in
Okay.
the middle.
And Q is the reference.
Yeah, Q is arbitrary reference vector. In this case, it has to be like that. So I guess they don't exactly agree, but this the Vichy-Flat tensor and the form looks
Yeah, it's the
exactly
same structure,
Yeah.
different Q vector, different reference vector.
Yeah.
But the reference vector wasn't supposed to be physical anyway.
So this is what we should look at. And remember, we only do this when when the fermions are in singlet. So the the spin configuration of here should be contracted with epsilon, which can be written as this up and lower contraction. And I can move the rho vector to the other side and write it as a trace. Now, let's look at this expression in the center of mass frame, which the photon only has time component in its momentum. Because of this Vichy-Flat tensor, if K only has time component, then the others must have spatial component to give a non-zero result. So let's look at the spatial component of this thing, which the sigma matrix just becomes the Pauli matrix for the spatial component. Let's look at just one of the term. For this term, in the center of mass frame, the momentum of particle 1 and 2 are just parity conjugate to each other because they have the same mass. So for parity conjugation, you just change the square spinor to a angle spinor. And the contraction of SU2 index for angle spinor just gives you the mass of the particle times a unique matrix. And we all learned that Pauli matrices are traceless, so it gives 0. And it means that even for singlet configuration, it can conserve JPC, but the amplitude or the residue should be 0. So if you look at a single photon channel, all the residue of electric particle to magnetic particle should vanish. And that conclusion is not new. It has been shown using Lagrangian. But in the constructed method, you are looking at just 5 lines of calculation, and it is like 5 pages in Lagrangian. So here we show that the constructed method can produce the same result and in a nicer, cleaner way. So, but so far, that's the work we have done using constructed method. For the next step in the future, we do want to calculate the total cross section of producing these monopoles in the LHC collider. We learned that single photon doesn't work, so we need to merge at least 2 photons, or a photon, a dark photon, or a pair of dark photons. So to calculate total cross section for proton-proton collision, because proton is a bag of all kinds of particles, you need to use this proton distribution function to capture the short distance physics of proton collisions. And for our purpose, we want photon-photon fusion. So maybe we can start with the photon PDF, and there are photon PDF available, and there's even dark photon PDF available. So maybe we can just start from the photon and dark photon PDF, and just sum over A and B to be photon and dark photon, and get a total cross section. That is maybe a way, but as I mentioned earlier, there's a phase difference between connecting electromagnetic particle using photon or dark photon. This formula will only works when the factorization theorem holds, which means that the interference between different partons doesn't matter. But here, we see if the partons are photon and dark photon, and switching from photon to dark photon gives you a minus sign, then the interference of different partons will matter a lot. In fact, the interaction between using a photon channel and dark photon channel is almost the same, besides the fact that dark photon can have a mass. So if the dark photon is massless, they will just cancel and give you 0, which will not be captured if you just start from the PDF of photon and dark photon. Yeah, so the difference.
Dark photon with the vertex as an epsilon. Where are all the epsilons?
So for the photon, the epsilon will be here. So this will be epsilon squared, and epsilon squared. The coupling is in the same order for all these 4 contributions. Yeah, so the difference is caused by the propagator, which have a minus n squared for dark photon. So if you add a photon and dark photon line, it gives you some contribution in order of mass squared. And here we are combining 2 lines, so together it should go like mass to the 4th. And this cannot be captured if you just use photon and dark photon PDF. And so one way is to actually calculate the 6-point amplitude and start from the quark PDF, but it's a 6-point amplitude. At least Mathematica is not doing that for me. It has been a while and it's not responding. So so far we haven't get the 6-point amplitude yet. It might be possible to use constructive method to get a 6-point amplitude, but that is future work. What I can do right now is to estimate the contribution using the fact that the difference between these 2 amplitude from photon-photon or photon-dark photon is just from the propagator, which, if the collation scale is a lot bigger than the mass of dark photon, can be approximated like this. So I can just write the interference effect into the contribution from just the photon-photon fusion times this factor. And this will be valid if I just look for the parameter space, which the dark magnetic monopole mass is way more bigger than the dark photon mass. Because if the dark monopole is very heavy, then the collision scale must be bigger than the mass, and therefore the collision scale will be way more bigger than the dark photon mass. So we can just look at this region for now, which we only need the photon PDF, and we can just use a 4-point amplitude, which has already been calculated by, again, John and Chris. This is the spin sum, and this P and Q are just, so this Q is not the same Q, but these are the momentum of the particles, and M is the mass of the dark magnetic monopole. So, yeah.
Which P and Q are which?
Sorry, so maybe I should retype this instead of just putting a screenshot. In here, they use P for my K. P is the sum of P1 and P2. K is the difference of initial particles momentum, so it's like P1 minus P2, and Q is like P3 minus P4. Maybe I should type it out myself using the same notation. Yeah. Anyway, the 4-point amplitude is there, and we do have photon PDF, so we can do this estimation. The physics of dark photon mass is just put in by hand like this, but it should be valid if we look at this region. So what we get, so let's look at a parameter space. This is the parameter space that have been ruled out or will be ruled out in future experiment from this paper. And here the horizontal axis is the dark photon mass, the vertical is the kinetic mixing square. So let's be optimistic. Let's say maybe we can look at this region, which haven't been ruled out yet, but can be probed in future experiment, and maybe we can find dark photon, and what we are doing is relevant. So this is something like 50 GeV for dark photon mass, and the coupling is like 10 to the minus 2 or 10 to the minus 3, because it's square. Yeah. So if I just plug in those numbers and calculate the total cross section by writing my own code instead of MATLAB, because so MATLAB nowadays just package the whole thing such that you just input the Lagrangian and they do the rest for you. But as I said, the Lagrangian we have is involving an vector, which the mathematical package they use, the phi rule, is just not handling the Lagrangian. I know in the old days people can just feed the amplitude to MATLAB, but that version is no longer available online and they're not maintaining it, so that's why I need to write my own code, and it's actually just integrating over the PDF and final phase space, so it's not that hard. And if I choose the beam energy for the proton to be that for the LHC, it's about 7,000 GeV, and I choose the kinetic mixing to be 10 to the minus 2. In here, I fix the dark photon mass and see how the dark monopole mass change the total cross section. And here I fix the dark monopole mass and change the dark photon mass. And here I just fix dark photon mass to be 50, and the dark monopole mass is like 3,000 to 7,000, which is like 100 times bigger than Higgs mass. But I choose this range to show you that when the dark monopole mass goes beyond the beam energy, the total cross section should drop to 0. So this makes sense. And for the graph here, I choose dark monopole mass to be 2,000, which is still like 10 times heavier than top clock. But we need the mass to be way more bigger than dark photon mass. That's why we choose this parameter. And you see, of course, it grows with dark photon mass because this mass to the power of force is put in by hand. It's definitely going to work. But the estimation should be correct, which turns out to be something like 10 to the minus 16 femtobarn. The integrated luminosity for LHC round 2 so far is just 150. So if we are looking at this parameter space, there's no way we have produced any monopole yet. But this is just like one point in the parameter space. There might be some other interesting region that is relevant for future experiment.
Which wins you more in the cross-section, decreasing the monopole mass or increasing the dark photon mass?
Say that again?
Which gets you a bigger cross-section, decreasing the monopole mass by a factor of 2 or increasing the dark photon by a factor of 2?
So this is 4, so it's 16.
Suppose if you go down M to 200 GeV, forget about it's not much bigger than photon. Just naively apply the cross-section with it.
You mean look at the graph?
Yeah, just say if I have a monopole 200 GeV, what would you get? Even though you worry about your approximation may not be good, just naively apply it anyway.
So it looks like a straight line here, which
200 GeV.
let's say here to here by half, and this is like 9. So 2 and 9, this is let's say 16. So 9, 4, 36. Yeah, if you follow this trend, then at 200 GeV, you can have a total cross section that is like 10 to the power of 3 or 4 femtobarn.
10 to the 3 or 10 to the minus 3?
3. So, I mean, here, this is 6,000 to 300. So this is
Okay, so you need
one
to make
half.
a new plot where the cross section gets
weird. Or,
gets above a tenth of a femtobarn.
Yeah, probably that. Go down to m. It's okay.
okay.
As long as m is bigger than m gamma, it's fine. I mean, you know when in the last part you don't trust it, just
Yes.
point
Yeah.
out.
This is just an estimate, so first you want to find where it's possibly worth doing the calculation, or maybe no place where it's worth doing the
Yeah,
calculation.
this range is hopeless.
Yeah, I mean, so you see the cancellation between interference of photon and dark photon is brutal. It kills a lot of cross section. Yeah. This kinetic mixing is not small compared to other experiments, but still the total percent is small. Yeah.
So when you do photon fusion, is there a regime where one photon has much more momentum than the other? It must be.
That is captured by the PDF.
Yeah.
But then, so you're approximating that things are canceling with a single propagator, but if in each of the sub-processes, like one has more momentum than the other, then the
But then you
cancel.
can always go to the center last turn, right?
Yeah, so there might be ambiguity from going from k squared to q squared. So if you want the exact result, I guess we still need this-point amplitude.
I'm just trying to see if it's worth doing 6-point amplitude.
Well, if there's just a factor of 2 or 3, then it's not going to show up in this low graph, or it can just
I mean, looks like the bounds go away at 50 GeV, so if your dark photon is 100 GeV, then there's no bound on epsilon.
This is dark photon.
is
Yeah.
dark photon mass.
Yeah,
in
that's what I'm
GeV.
saying. If dark photon was 100 GeV, then epsilon is arbitrary, no bounds.
I have to look for the papers to see if there's anything out there.
I think photon.
That last point looks like it's pointing up.
Yeah, here's the experiment that rule out the thing. In this
Yeah.
class, there's nothing there so
Yeah,
far.
well, yeah,
But that
so-
blue line, LHCb, mu prompt,
Yes,
that's not a bound.
that is future bound. I don't think they have done
They also
What's dark light? That's a future.
the. So if the area is shaded, I think that is the experiment that have been done. All this line with no
Okay, so
fielding should be future experiments.
so epsilon
also
could be.
it's left bound, right?
But there won't be a bound on 100 GeV dark photon from left, right?
Huh? This, yeah, left bound is complicated. Because you left go up to 200, what? 208 GeV. Yeah.
150 GeV.
Huh?
150 GeV dark photon.
Then, let's see. Sorry, what do you look for in your slider? You go to dark photon and dark photon to what? To
It's
You
usually
make
back and
quirks,
forth.
right?
Or-
Make quirks that have tiny couplings to photons.
the bound depends on the signature, right? What are you looking for?
So for dark photon, people look for
Meaning,
only 5.
first, of course, we have precision bound, right? For Fermi interaction. That bound is just go back to standard model. Standard model, not photon. Back to standard model. So that's coupling to the fourth tau, right? That one is constrained to what? 10 to the left. 10 to.
I mean, it's just a normalization of the photon interaction. And the
No, it's left 2 bound, right? Your dark photon is heavy. So it's the whatever in this W or Y
yeah.
bound. That's right. That's typically you need that 10 to the minus 3-ish, close to the minus 3, probably coupling square. So it's 10 to the minus 1.5-ish, something.
I'm not familiar with full
Point,
Fermi.
point 1 or point, point 03 maybe, something.
I'm not sure. I am not familiar with full Fermi.
Just the left 2, do you know left 2?
Not my.
I'll have to find out by Friday,
Yes. Okay.
because he's going to ask.
Yeah, what's W? And the Y and W parameter.
W is T3 minus sine theta squared or something like that.
It's the Barteri, Ratasi, formula, and the spinor or the formula.
W parameter.
Yeah, we'll discuss this afterwards.
Okay. So I'm done. We show that conservative method can be applied to amplitude with magnetic charge. We estimate the total cross section using photon PDF for some region, but there's still a lot to be done.
That's at minus 2 for this heavy one, I think it's fine, but you probably cannot make it much bigger than that.
Okay, first we're thanking the speaker. More questions? Yeah, just in general, you need to find some parameter range where the cross-section is big enough that we can probe it, right? So it
we
needs
can
to
draw
be
some
more than
empty
a...
space.
If you make a monopole heavier, lighter than a dark photon, isn't that better? You don't have the interference anymore. Of course. Is that
Well, it's better maybe, but the calculations are harder because
can you just ignore the dark photon contribution in that case?
I mean, it's like when a dark photon is lighter, then you can do some non-relativistic quark model to find the bound states. But when the dark photon is heavier, it's like finding the pion. It's like having massless fermions that are confined in a potential. It's a relativistic bound state. So you reduce the hand waving.
But, I mean, at least for production problems, you just do the photon fusion.
Yeah,
without
but,
the
right.
photon.
But
Then,
to find the signature, what are you looking
after
for?
that, what do you find?
Well, it depends on the structure of the bound state.
Then you have this dark monopole.
Can we kind of harmonize if we keep moving?
Hmm?
can kind of hadronize, like you pull it longer and then the dark photon just generate a new pair of dark monopole and then
When the dark photon is heavier than the monopole, yeah. But you don't have any data on how that happens, and you don't have any computer simulation of how that happens, so
I think at least you need to produce them first to worry
Yes.
about signature.
first you have to find a region in parameter space where it's possible to produce them. If you find that, then you can try to figure out what the phenomenology is in that region. And it seems like there's not a very large region, or maybe no region where
well,
you can produce them.
I haven't tried to find them yet. It's,
Yes.
You just need to make monopole quite high, right? It seems that you are going in that direction. Right? You don't want to light dark photon, but you want to light monopole, to enhance the perception.
yeah.
For a collider search. I mean, for Nancy's tabletop searches, there's probably a different optimal region to look for. I guess there's no further questions. Thanks, Hsing, again.